talking about parent functions, and then we're going to use our parent functions in order to review all of your skills of transformation. So you should have last year kind of talked about transforming quadratic functions and cubic functions, and you kind of moved them around a little bit. You talked about how to shift them up and shift them down and left and right, maybe kind of a little bit.
I thought that was geometry.
That was geometry. All right, so it might have been once school shut down, so maybe it was not in your brain so much. It's gonna be okay. We're gonna get it in your brain. But before we do that, we're gonna talk about parent functions, which is basically just the basic shape of the graph. It's like the most standard shape. It's the easiest form of the equation that we can give you. Recognizing the standard shapes allows us then to move the shapes around when they change the equation or they transform the equation. So all we're doing today is basically playing like I Spy and matching. We're actually going to physically play Simon Says, yes. But I'm going to give you either the equation or the name, and you're just going to show me the shape of the graph, which is also up at the front of the room to help you. So it is kind of like I Spy. So our parent functions are they're the most basic form of a graph or equation. They show us the general shape of each graph. Do you want me to turn one of the lights off? Let me turn both the lights off? No. You're right. All right, so this is going to be like rapid fire. Here's the name of the graph. Here's the function of the graph. Here's what it looks like. Because that's what we need in your notebook so that you can play this game. So this is a little bit lengthy because there are 12 of them. But we're going to do it as quickly as possible so that you can have fun.
Great.
Deal? Yay! All right, so the first one that we have is our constant function. Take note of the little guy on the side who's sticking his arms out straight to the side. Constant function, our constant function is written f of x equals c, where c is any number. So it could be 5, it could be 7, it could be negative 300. C is just a number. And when we graph our constant function, it's just going to be a straight line at whatever our c value is. So constant function is always just a completely flat straight line.
Always on the y?
Always on the y, yeah. Because it's always going to be like, f of x is our just fancy way of saying y.
Equals.
Yeah, so it's y equals some number. So we find that y value, and then we just draw a straight line through it.
Why do we write f of x instead of y?
Because it tells us it's a function already. Yeah. So if Simon were to ask you what a constant function looks like, you're going to go. See where this is headed?
No.
All right. Our second one, linear function. You've already seen this bad boy. Our linear function is everybody's favorite, y equals mx plus b. But we want the most standard form, so that means we're going to have a slope of 1, we're going to have a y-intercept of 0, or we're going to have f of x equals x, just x. So you'll notice our parent functions don't really have, we're not adding or subtracting anything, we're not multiplying by anything. We're as straightforward and as basic as we can possibly get. When we graph a linear function, our standard linear function goes right through the origin with a slope of 1. That's the one you have seen over and over. That's like the first thing you ever graphed back in Bolger, right? That's our linear function. We start to get a little fancier as your math career progressed. You had a quadratic function, which was f of x equals x squared. Do you remember what that graph looked like? A parabola. Yeah, it was a U. It was a parabola. Let's see if this will let me be fancy. Yeah. It was a parabola centered right at the origin. Ready for number 4? The square root function. So now the square root function is the inverse of our quadratic function because it's the opposite, right? In order to undo a square, we use square root. So these are it's an inverse. Our equation looks like f of x equals the square root of x. Now that'll be a nice easy one to pick out because it literally has the name of the function is a symbol in the equation, right? You can see the square root there. Mm-hmm. Yeah. It also, when we graph it, it kind of looks like a square root symbol. It starts at the origin at 0, 0, and it just kind of looks like if I took a parabola and tipped it sideways and cut it in half, yeah, because I don't want to use both sides of the parabola if I tip it sideways, because then I'm not a function, right? It's failing the vertical line test. So I'm only using that left side. What's that?
So even unless it's going to the left, same thing.
So if it's going to the left, it's still a square root function, but it would be negative.
Yeah.
Yeah.
That goes to all of them except for like linear and.
So and that's what we're gonna do. That's our next step once we look at all these shapes, is actually moving them and seeing, because you've seen linear functions that go downhill before, right? Yeah. Right. So we can take these and we can move them all around, but we would still classify their parent function as one of these 12. Yeah. So it can absolutely face the other way. That's just going to be one of the transformed versions of it. The parent function has to go to the right. Number 5 is the cubic function, which you may have seen this one last year. This may have showed up when we were talking about polynomials last year. It's normally the one that comes after learning about quadratics. And it's just x cubed, or x to the 3rd power. And when I graph it, it also kind of sits right at the origin, and it looks like a parabola on the right, but then it kind of looks like the parabola broke and fell over on the left. you seen that one before?
Mm-hmm.
Okay.
Well, what if it's like full, like.
That's to the fourth then. X to the fourth
means
power.
they're
I know, but I'm saying like instead of being a cubic function, what would it be?
Once they start to have more powers like that, we just call them polynomials.
Oh, okay.
Because I can keep counting. I can up that power every single time. So what happens when I up that power is it starts to have it like bounces up and down that many times. And we're going to talk about that when we talk about end behavior in our next section. But for now, you only got to worry about x squared and x to the third power. Then our inverse, or our opposite of a cubic function, is a cubed root function. And that's f of x equals, do you remember how we denote cubed root? Yeah, that little 3. It's also on the screen, right? A little cubed root of x. And this one's graph looks like I took the cubed root function and just tipped it on its side. What if I asked you the domain of this function? What would you tell me? If you had to dust off those skills. Yeah, negative infinity to positive infinity, right? It's going to the left forever, it's going to the right forever, negative infinity, positive infinity. What about the range?
It would stop.
Same thing.
Same thing. It's even though it looks kind of flat, it's
still
just slowly growing. It'll slowly grow up and up and up and up forever.
Oh.
So that still has a range of negative infinity, positive infinity.
Those-
It's just we're gonna have to get really, really big x values in order to get big y values. What about absolute value? Have you seen graphs of that bad boy?
It's the V.
It's the V, right?
Yeah.
Yeah. Which kind of makes it easy to remember. Its graph, or its equation, is easy to pick out because it literally has those absolute value bars right in it. And the graph looks like the V.
I definitely don't know this because I looked at this line.
The V is centered right at the origin. And those lines have a slope of 1 on the right and negative 1 on the left. Makes it V for value. Makes it a little bit easier to remember. What would the range be here?
0 to infinity.
0 to infinity, right? And when we wrote that, we would use a bracket on 0 because it's included.
Mm-hmm. Yeah.
And then this might be one of the last ones you've ever seen. Exponential function. We talked about this with things like how your bank account grows, the interest rate in your bank account. You might have talked about it in science class with population growth or how animals are becoming extinct, things like that. This function, when we talk about it, we're going to say f of x equals, and now we can use any number. We can use 2 to the x, we can use 7 to the x. Our base can be any number. Our x is going to actually be our exponent though. So I'm going to use e to the x because I like the letter e for exponential. Looks exponential, right? And e is actually a fancy number that we're going to talk about later in the year. It's like pi, how pi is 3.14. E actually is 2.71. And it's going to come up later. It's like a super fancy exponential number that we're going to use. So for now, we'll just use it as a symbol to represent a number.
Is it a letter or a number?
It's a letter E, but it represents a number.
Oh,
Yeah, it represents a number. It's like how pi It's just a symbol that represents a number.
That's a symbol.
Yeah. Well, pi is a Greek letter. Yeah. And when we graph this, it actually has an asymptote. Do you remember that word? Asymptote is an imaginary vertical line or horizontal line that the graph cannot cross.
Mm.
So this one has an asymptote right at 0. So when I actually graph this function, it looks like this. And this is a graph that flattens out and isn't ever going to cross that 0, the parent function. If it helps, this point right here is 0, 1, and then it kind of just curves up. So knowing that it has an asymptote and it doesn't ever go below 0, if I was writing the range for this, what would I say?
0.
0, not including.
Right. So my range here is 0 to infinity, not including 0. Which is kind of tricky because we're used to, even though our graphs maybe like our cubic function, it looked like it kind of flattened out, but we knew it kept going forever. This one actually does flatten out. All right. Next one we've got is a log or a logarithmic function. Did you talk about logs last year? A little bit, right? So we're going to talk about them some more. Our log function literally says log in it. Log of x. And when we graph our log function, our log is actually an inverse or an opposite of an exponential. So they kind of look similar. But just like we saw with the quadratic and the squared, or the cubic and the cubed root, it's like I'm taking it and tipping it on its side, kind of. So now my asymptote goes down x equals 0, goes right down this middle line. And when I graph a log function, my log function is never going to have a negative x value. It also goes through the point 1, 0. So here, my domain is 0 to infinity. So I can't have negative x values. My exponential, I couldn't have negative y values. For log, I can't have negative x values. All right, 3 more. These are the scariest ones, but it's all going to be okay. So after we talk about exponential and log, then we're going to dust off everybody's favorite geometry skill, sine, cosine, and tangent, and we are going to also graph those. So when I write an equation for sine, it looks like f of x equals sine of x, and our abbreviation for sine is SIN. Notice that I put parentheses around the x, so what's happening is that x is being put inside of the sine function. So sine is like a big fancy function that shows up all the time, so just like we write f of x or we write g of x, they gave it a specific name and they said, okay, we're going to call this the sine function, and we're going to plug numbers into the sine function. So it's not saying sine times x. That's telling us to put x inside the sine function. When I graph that, what you need to know for now, when I graph it, my sine function starts at 0. It goes up to 1, back down to 0, down to -1, back to 0, and as I continue on, it just repeats that pattern where it goes 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, blah, 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 over and over and over. It'll also do that as I go backwards, so my pattern just kind of repeats. If we were in science, they would tell you this was a graph that was oscillating, which just is a big fancy word for bouncing back and forth. And as it bounces back and forth, it can continue on and on forever. I can have as many x values as I want. So if I was looking at this graph, I would say my domain.
Please pardon the interruption. Any senior who is planning to apply to Rutgers, please report to the auxiliary gym with their Chromebook at this time. Any senior planning to apply to Rutgers, please report to the auxiliary gym with your Chromebook. Thank you.
Oh, man. I think they just posted it on your Google Classroom for this morning. Nobody else?
Should I take my stuff?
Probably.
I'd say yeah, because it's a lot of things. Can't hurt.
My range here, what was the highest I ever went? 1. What was the lowest I ever went? Negative 1. So my range is just negative 1 to 1.
Very simple.
Not too bad, right? So with sine, we know, comes cosine.
You gotta get your book.
I know.
Isn't cosine just the inverse?
Somewhat. It's actually a transformation of it. So when we graph cosine, or when we look at our equation for cosine, I get f of x equals COS is our abbreviation for cosine x. And when we graph this, it actually looks almost identical to the sine function. The only difference is the pattern instead of starting at 0, starts at 1. So I start up at 1, then go to 0, then go down to 1, 0, 1. So it actually is exactly the same shape as our sine graph. It's just moved over. So instead of going straight through the origin, it starts up at 1. So that's the big difference. The sine graph goes straight through the origin, whereas the cosine graph starts like right in the middle of that hill. So it still has a domain of negative infinity, positive infinity, because I can plug in every x value I want, but its range is still negative 1 to 1. It just looks like I kind of shift it back a little bit. All right, last one, and then we can play our game. Reciprocal function. Reciprocal function is f of x equals 1 over x. And when we graph it, you've seen this one already. When we talked about domain and range, when I graph this, our reciprocal function is the one that's broken into 2 pieces. It has an asymptote at 0. And at y equals 0. It's that graph that had the 2 separate pieces when we talked about domain and range. I think it was your challenge problem for domain and range.
Yeah, it was like you had to exclude every number.
Yeah, exactly. So the whole idea behind all of this is that next class we're going to start moving them around, because our ultimate goal is that I can give you an equation and you can graph it without using Desmos or without using a calculator. That's our ultimate goal. So by knowing what their general shape is, then when I say, okay, shift it up 1, you know what the shape already is, so you take that picture and you literally move it up 1 on the coordinate grid. If I say, okay, stretch it, you're just going to make it taller. So it's kind of like we're taking art class and putting it in math, because you're going to know what the pictures are and then move them around. Cool. All right.